Today we're going to be talking about one of the most important aspects of your camera, the lens. Hey fellow photographers, what did you shoot today? So the lens is a really important part of your camera. It's a transmissive optical device that will either focus or disperse light based on the rules of refraction. So we're going to start off simple, talking about simple optics, and we're going to talk about, one element lenses. Obviously the lenses in your camera are much more sophisticated, but we're going to, because of this is the Science of Photography channel, we're going to start off slow, and then we're going to introduce some math on the blackboard and see how the properties of lenses work, and then we're going to talk about some more complicated designs in future videos. So this concept of refraction is really important. Essentially, the wave theory of light says that when light interacts with different materials or different surfaces, there's going to be a manipulation of that light. Kind of like when you see a glass and you're looking at the glass and the straw seems like there's a kink in the straw. We know the straw is straight, but when we see it through glass or water or different types of media, then the light seems to bend and it sort of tricks our eyes. So the wave properties of light lead to Fermat's principle of least time, and that in turn leads to something that we know as Snell's law. So we can think of it like this. Let's say we have a surface, like so, and we have light rays that are interacting with this surface. So we'll call this a light ray. And we can call this air. Let's say this is just the air around us, and let's say that this is a glass surface, like you would see in a lens. Now, what's important to know is that these different surfaces have different indices of refraction, and that's going to determine how the light behaves when it moves from one surface to another. So for the purpose of this, we're going to throw some numbers out here. So the index of refraction of air is about 1, and the letter used to denote the index of refraction is n. And for glass, let's just say it's 1.5. So water is about 4/3 or 1.33. Different types of crown glass is around 1.5. So these numbers are fairly accurate, but it's just going to give us an idea. So what's happening is that the light in air that's moving through the air, propagating through the air, is going to interact with a surface that has a higher index of refraction. So in order to study the interaction between light as it goes from air to a glass surface, we're going to draw a normal line. This is just a perpendicular line to this surface. And if we have this light beam coming in, we're going to call this angle theta 1. And what we're curious about is to see what happens to the light as it leaves this surface. Now, because air has an index of refraction of about 1, and glass has a higher index of refraction, when you go from a surface from low to high, what's going to happen is the light is going to bend inwards towards this normal line. So you would think that this sort of ray might continue in this direction. That's not the case. What we observe is that it actually bends inward. Now, it doesn't change color like this. I'm just making this for illustrative purposes. And this will be theta 2. So this angle is going to be smaller than the original angle at which the light hits the surface. So Snell's law gives us an expression that describes this relationship. I'm going to write it down. In a future video, we're going to derive it so you know where it comes from. But for right now, let's just take it as fact. So Snell's law states that n1 times sine of theta 1 is equal to n2 times sine of theta 2. Now sometimes you'll also see this rewritten just by rearranging the terms. We'll move sine of theta 2 to this side and n1 to that side. So you can also see this written as sine of theta 1 over sine of theta 2 is equal to n2 over n1. So these are both equivalent. And what it says is that the index of refraction of one material times the angle at which this light ray hits it is going to be equal to the index of refraction of the second material times the sine of the angle of this light ray. So if we know at what angle this is hitting and we know the indices of refraction, we can calculate the angle once it reaches, once it goes through the glass. So we're not going to go into details about how to derive this just yet, but maybe I can draw a different diagram that will explain why this might be the case. So instead of air and glass and all that fancy physics stuff, let's just think about a different scenario and kind of explain why we don't see light pass straight through a barrier or some material. So let's say we have 2 points, A and B. Now, you might think that the fastest distance between A and B is going to be a straight line. And if these are light rays that we're traveling, you would think that the shortest distance between A and B is a straight line. Well, that's not necessarily the case, and here's why. Let's assume, like we did before, that this n1 is equal to 1 and n2 is something greater than 1. So we could make this 1.5 like before, but we just know that it's greater. So as it turns out, this straight line is not the fastest path that light can take between these 2 points. And the actual path is going to be something kind of like this, right? It's going to have this kink. And why is that? Well, because this has a lower index of refraction, light is actually propagating faster through this material, which is air in this case. It's actually traveling faster than it is when it is traveling in water or glass or anything with a higher index of refraction. So actually, this is based on the principle of least time. So the time it takes light to travel from here to here, bend and then go to here, is actually shorter than if it were to go the whole way. Now, that might not seem intuitive, but let's just maybe put an example to it. So let's look at an abstract example and see if we can sort of draw some analogies between why this behavior exists, why we see this kink in this graph. And you might have heard problems like this in physics class and whatnot, but it's the same concept. So let's say that you're going to the beach, right? You're on vacation and you're going to the beach, and here's you at point A, and you had to park your car a couple blocks away from the beach. And then you want to walk to the beach, right? And this is where the sand starts, and then you want to get to the water. You can't wait to go swimming in the ocean. So you're up here, you park your car a few blocks away, and then this is all concrete, sidewalk, and asphalt, and that kind of stuff. And you can walk, a relatively good pace on concrete because it's smooth. But once you hit the beach, right, and you hit the sand, it's harder to walk in, right? It's harder to walk in the sand. So it takes more effort. So what happens is you walk a little bit faster going through the asphalt than you would the sand to the beach. So why is it that this becomes the shorter distance, right? This kink doesn't look like it's shorter, right? Because it looks like it's longer than if you were just walk straight. But you have to take into account how much time it takes you to walk from one place to another. So if you were to walk here down this straight line path and then down to the beach, it would actually take you a longer time. Why? Because you're not taking advantage of the fact that you can move faster through walking on the sidewalk than you can through walking through thick sand to get to the beach. So what you want to do to get to this point, you actually want to, this is basically broken up into vertical and horizontal components of your sort of velocity, your walking speed. And you want to spend, there's an optimal amount of time you want to spend walking in the fast zone where the index of refraction is less. Glass, concrete and sand don't really have indices of refraction, but you get the idea. So you want to spend more time, or you want to get closer to point B this way, when it's easier for you to walk than when you're walking in the hard sand. So that's kind of why that happens. Now, that only occurs, this sort of kink happens when you are moving from a low index of refraction to a higher index of refraction. Now, if you're going the other way, right, you're basically following the same path backwards, right? But again, when we talked about Snell's law, we're drawing the normal here, right? This is our normal. So it's important to know that we want to spend more time, or less time technically, we want to spend more distance, more walking distance in the faster media. So when you're going from a low index of refraction to a higher index of refraction, this angle, theta 1, is going to be greater than theta 2. And we can also think of this as you approach this normal, you're going to bend towards the normal, going this direction. And when you're going this way, when you're going from a high index of refraction to a low index of refraction, when you hit this plane, you're going to bend away from the normal. So just remember that. Low to high, we're bending inwards. High to low, we're bending away from this normal line. Now let's see how this affects lenses. So in photography, we're most concerned with focusing an image. So we're going to use a lens that will focus light rays. This is known as a convex lens. And this will converge light rays. Now, this what I've drawn here is actually a biconvex lens because each surface of the lens is convex. So this is a biconvex lens. Now, here's the middle of our lens. Here's our sort of optical axis. Now, I want you to take a look at why a lens that is of this shape, using what we just learned about indices of refraction, is going to focus an image. So what I'm going to do is I'm going to basically, imagine if I took just this top area here and we're going to sort of, get a bigger picture and sort of enlarge it. So let's say that this is that enlarged view, grossly exaggerated view of this top of this lens. So we have these curved surfaces now, right? And these are, we know this is a converging lens because it's convex, but we want to know why. So let's say we have a light ray coming in this way. I'll draw it in red. So we have a light ray coming this direction. Now what's going to happen in this light ray is that it's going to interact with this curved surface. We can still draw a normal to this surface, right? It just has to be perpendicular. So this is our normal line, right? It's a right angle to this curve. Even though it's a curve, we can still draw a normal. And like we said, out here, if our lens is made of glass, so inside here, n is 1.5, and outside, n is equal to 1. So this is air going into glass. So remember, when we move from air, a low index of refraction, to a higher index of refraction, this line, instead of going straight through, it's not going to go straight through, it's going to bend towards the normal, this normal, when it interacts with this surface. So this light is now going to go like this. So the light comes in, hits this surface, bends towards the normal, right? So it's not going to go straight through the lens, it's going to bend towards the normal. Now what happens when it hits this other side of the lens? Well, we draw another normal. So this normal is now like this, right? We have a different normal for this surface, another right angle, a tangent, a perpendicular line, sorry, not tangent, perpendicular line to this surface. And now look what happens. We're going from 1.5, a high index of refraction, to back into air, a low index of refraction. And we said from before that this light ray that comes in from a high to a low is going to bend away from the normal. So it's not going to continue straight like this. It's actually going to bend. It's not going to be like this. It's going to bend even further away from that normal, something like that. So you can see that both of these surfaces are actually bending this light inwards. So we come in like this. We're going from low to high. We bend inwards. Now we're going from high to low, and we bend away from the normal again, but overall we're still bending, we're converging this light ray down here. So how does all this relate to focusing? Well, let's take what we just learned about our biconvex lens, and we're going to assume that this is what we call a thin lens for now, because we can make some thin lens assumptions. And basically what happens is that a lens like this, that is convex, or any lens in general, that's the middle of our lens, is going to have some sort of focal point, right? So let's make this, the lens's focal point F. So what's going to happen is that all the light rays that are coming in are going to sort of bend towards, they're going to converge to this focal point, but they're going to do so in a particular way. So if we have our focal length out here, and this is a biconvex lens with each, with symmetry, right? So there should be we can put another focal length out here. And let's just say as the observer, you'll see this a lot. People will put like, an eye like this. So we're looking this way. Now, we can use this lens to focus an image, right? So we can put, some sort of film plane out here somewhere, and we can put an object out here, and we can see how this lens will actually create an image. Or maybe it won't, it depends where the object is. So these are popularly known as sort of lens ray diagrams. So there's a lot of different scenarios. So usually they're drawn with little arrows. So we have an object, right, out here. This is like our little happy tree from last time. We can even make this a little tree if we want. So we have a tree out here. Happy trees. So we have a tree out in the distance, and we want to know what happens to this tree as it is focused by this lens. Well, there are a few rules that we have to go over. One is that light rays that enter or hit this surface sort of parallel to the optical axis. So that means that light rays that go this way, they're going to go straight across, parallel. And I'm not going to draw the individual bending here, so we're just going to assume, because it's a thin lens, we're going to assume that it just kind of meets at the middle here. So light rays that come in parallel are going to bend and be focused through the focal length of the lens. So that is where that light ray is going to go. Also, another rule is that basically if you can use sort of the opposite, right? If you have a light ray that goes through the focal length of the lens, it's going to come out parallel to the optical axis, something like this. And there's a third rule that says that a light point that goes through the center of the lens is not refracted at all. So this kind of goes like that. And these all converge way at the edge of the chalkboard, because I didn't draw this very well. I didn't plan ahead. But essentially what's going to happen is that there's going to be an image out here. So we're going to stick with arrows because they're easier to draw than trees. So right out here is where that image is going to be. And here we see something very interesting, right? The image of the tree is actually upside down, and in this case it happens to be bigger than the original image of the tree. So this is one example of a lens ray diagram that explains sort of why you get an inverted image when you look at a lens. Now the lens I was holding up at the beginning of the episode was also biconvex. So if I have something like ABC and I hold up this lens, we can see that it is upside down due to the biconvex lens, that is basically this thing right here. Okay, so similar scenario here, same type of biconvex lens setup. The question becomes, what happens when the object that we're interested in is actually placed at the focal point of the lens? Well, remember our rules, right? So anything that goes off parallel is going to be focused through the focal point, like that. It's going to be bent towards the focal point. Now we can't go through the focal point and go, parallel, because we're just going straight down, so that doesn't really make any sense. But we can use our other ray here that goes through the middle of the lens. And if I drew this well enough, we notice that even if you extend these rays backwards like this, that they're basically parallel, right? So an object that is here at the focal length is not going to produce an image because these don't converge to any point. So this is important for different things like minimum focal distance for lenses. Now, of course, you don't have one element lenses, and your lenses are much more complicated than this. But you can kind of see to understand why, if you put something too close, it's not going to even form an image. It just might look like a blur of color or something, because we're not going to see, even if we're looking this way, our eye is down here, and we're looking at this, we just see these beams of light. We don't see an actual distinct image because these points of light are not being focused to any particular point. There's a third example, which is also very interesting. So if we draw our lens one more time, real quick. We have a focal point out here. It's symmetrical out here. What if we have an image that is so close to the lens that it's within the focal distance of the lens? Well, another interesting thing happens. So we're still going to get this line that is going to go like this, parallel and then through the focal point. And we're still going to get this that goes straight through, but now these are not parallel, they're not converging. We can also draw a line that actually goes through this focal point like this, and then goes off parallel. And what happens is if we basically imagine these rays going the opposite direction, like this, they actually all meet. And we use dotted lines because this is going to be a virtual image. They all meet at this point here. So the new image is actually on the same side of the lens as the object. It's not flipped, it's upright, and it is what we call a virtual image. Now, I can also demonstrate this with the lens that I was holding up earlier. And this is kind of what a magnifying glass would do. So if I get this very close to the lens, as you can see, it's going to be blurry, but if I move this out, it looks like the image is bigger, right? It's not necessarily focusing, but it is basically making the image bigger. And this is what a magnifying glass would do. Now watch, as I pull this away, the image will actually flip upside down. Right? Because I'm moving past the focal length of this lens. So now we have an image that's upside down and flipped like normal. But if we have this very close, the image gets bigger. It's a virtual image, and it's going to be on the same side of the lens. Because if we're looking this way, here's our eye, our eye is seeing the light rays like this. It's seeing this light ray here. And all these light rays are converging to a point. And your eye basically is, conditioned to see a larger image here because it thinks that the light rays are actually coming from this kind of object. Even though this is a virtual image, your eye thinks that this is an object, and that's why it looks bigger, and that's how magnifying glasses work. So, to summarize, we have a lens. In this case, it's a biconvex lens. It has a focal point. It's symmetrical. It's a one-element lens. And depending on where we put our object, so let's say it's out here like before, we know that this is going to create some sort of, just do a quick and dirty diagram here. So here is our image, here is our object. So there's actually a very interesting relationship between all of these factors, and that is going to be sort of the thin lens equation, which is defined as 1 over the focal length is equal to 1 over dO, which we're going to call the distance to the object, plus 1 over di, which is the distance to the image. So this is, from here to the center of the lens, is F. Let's get some more colors. So F is in white. Distance to the object is going to be basically here to the center of the lens, dO. And distance to the image is going to be this straight distance from here to here. So this is di in green, di. Another important optical concept is that of magnification. And we define magnification as negative di over dO. So basically this is saying that this distance over this distance will tell us how big or small this object will be magnified, its image will be magnified. And this negative sign is going to tell us whether or not the image is reversed. If it's negative, it's going to be inverted, upside down from what our object was. And if it's positive, it's going to be like the other example where it was on the same side but a virtual image. So if it's positive, it's going to be in the same direction. It's going to be upright, like with a magnifying glass. But if it's negative, it's going to be inverted like this. So now obviously this is just a very big oversimplification. We're only dealing with one kind of lens. It's a single element lens. But this is going to give you an idea of how light behaves. Now, in future episodes, we're going to talk about different things that a single element lens, the problems that it can cause. Because this would be essentially much easier to manufacture than a lens that has multiple elements in it or has moving parts, like a zoom lens. So why aren't most lenses just single element lenses if they can focus light and produce images, right? Well, as photographers, we want the best image quality, and what we're going to discuss in future videos is that simple lenses like this actually introduce a lot of problems, optical problems and abnormalities that we don't see as desirable as photographers, because we want something that mimics the real world. Whereas our eyes are doing all the processing for us, a simple lens like this is actually going to do some pretty interesting things to light that we may not see as a sharp image, as a color correct image. It might have fringing. So in future episodes, we're going to talk about the limitations of these very simple lens systems and move into more complicated lens systems. So I hope you enjoyed this overview of optics. We're going to talk a little bit more about this. We'll do some example problems if you're interested. Let me know in the comments what you want to see. If this will help you with your physics homework or something, let me know. But we'll move on to different types of lens designs and the sort of the aberrations that they're designed to correct. And as always, until then, happy shooting. My battery's dead.